Hey everybody, we are going over the Ballooniverse pre-lab right now. So you should have a split screen on your Chromebook. One half you should have your document, the other half you should have this presentation. We are going to be pausing through the presentation to talk a little bit about galaxies. So here we go. All right, first of all, the first question was the Big Bang Theory. And you had to do some fill in the blank by scanning the text. Here we go. The fact that the universe implies that it had a beginning is very important. So that's the first step of the Big Bang. Letter B, the momentum of the outward expansion of the universe is opposed by the inward force of gravity. So it's trying to expand, but gravity is trying to pull it back together. So it causes the matter to slow the expansion. Letter C, when the rate of expansion of the universe is known, it is possible to calculate the time since the expansion started and then determine the age of the universe. So if you know the rate of expansion, you can calculate the age. We did that in the lab. Letter D, the value h, many of you couldn't find this because it wasn't in the book, is called Hubble's constant, and it is called the expansion constant. If this is known, if you know that constant, then the age of the universe can be determined. Letter E, based on the base value for letter H, which varies due to the expansion or fluctuation, the age of the universe is found to be about 13.7 billion years old. And finally, letter F. The age of the universe fits with what astronomers know about the Milky Way galaxy, which is estimated to be between 12 and 14 billion years old, based on the age of the oldest star clusters that we see out there and looking at composition, which we already did in a previous unit. So be sure right now on your document that you have these red letters filled in. And later on, when I send you a copy of this video, you can pause it and be sure you have these correct. Here we go. Number two, what are the three possible outcomes for the universe? So this is on page 680. I said explain each outcome using the word expansion. So for the first picture that you had on your document, that's called an open universe, meaning expansion will never stop. It just continues to expand and expand and expand indefinitely. A closed universe was the second image, and that's where expansion stops and becomes a contraction so that it goes back to the beginning again. So it means it expands, then it contracts and comes back. And finally, the last one is a flat universe where expansion slows over time, but it never eventually contracts. So there are three images here that you can see. This is the closed universe where it expands and contracts. The open universe just simply never stops expanding. And finally, the flat universe where it expands and it goes slow over time. So that was number two. All right. Number three, and sorry, I forgot about this, possible outcomes of our universe. So using those three models, if you take a look, you have in blue the closed universe, right, where it comes back together again. Flat universe is where it slowly expands. And then the open universe is it never stops expanding. So if we did the radius of the universe compared from now until, as time moves on, you can actually plot those different models on a graph. All right, number three, types of galaxies. Very important when we're studying the universe. Galaxies are simply defined as large-scale groups of stars and nebulae that are bound together by gravitational attraction, holding them together. So although those are the basic ideas of galaxies, they look very different. So here we go. Galaxy type number one is called a spiral galaxy. So spiral galaxies have symbols S, SA, SB, SC, or SO. And so they're very disc-like shaped, and they have a nucleus with a bright ball at the center. And then they have flattened arms that spiral out from that ball and kind of swirl around like this. So there are the letter A, B, and C, as you guys can see, an O after the letter S, which stands for spiral, means what do the arms look like? So in other words, if it's a little letter A, it means the galaxy has tight arms, which means the stars are really bound together. If it's a letter C, it means it has really loose arms, meaning the stars are scattered around the ball. And then finally, a letter O means it has no arms. Letter B would kind of be in between tight and loose. Finally, these types of galaxies are known to have very young stars, and they're rich in gas and dust. So as you look at the little image here, you can see this is an example of a spiral galaxy. There's the bright nucleus along with arms that extend outward. The nucleus itself is not one giant object. It is just stars bound tightly together by gravity that look like one object, but if you could fly through it, it would be separate stars. All right, the second type of galaxy, by the way, on your document, make sure you have the highlighted red words if you're doing bulleted facts. Those are the most important things. Disk-like, nucleus, arms, young, gas, and dust. All right, very important you have those. All right, the second type of galaxy we're going to talk about for number 3 is elliptical galaxy. These galaxies are symbolized by EO through E7. So, in other words, the rounder they are, they're EO. And as they progressively get more elongated or elliptical, like a football, they become E7. So, any other number in between would decide how squashed the ellipse is. So, these types of galaxies are very tightly packed. They don't have spiral arms, they have no young stars in them, and very little gas and dust. One half of something we're going to talk about in a moment called the local group are elliptical galaxies. So, once again, look at the image. This right here, although it just looks like some bright star, it is not. That is an entire galaxy. So, again, the keywords in red: no arms, no young stars, and little gas and dust for elliptical galaxies. Okay, the third type of galaxy is called an irregular galaxy. So the symbol for irregular is IRR. And these galaxies have no distinct shape. They're just stars kind of scattered all over the place. They have a very low total mass and they're very rich in gas and dust. They make up the smallest percentage of galaxies known. And if you look at the image, you have some bright stars in the foreground here, but you can see, look at all the gas and dust out here. So that is called an irregular shaped galaxy. And then finally, the fourth type of galaxy for number 3 is called a barred spiral galaxy. So a barred spiral galaxy has the abbreviation S, meaning spiraled, and then B for barred. So SB is barred spiral. Now, do they have little ABC? Yes, they do. And that tells you about the arms again. So barred spiral, keywords, they are disc-like in shape. They have elongated central regions, which looks like a bar that kind of spirals out. Look at the image here from the center. So the bar kind of spirals out on both sides here. So again, A means the tighter arms and C means the loose arms. And then if it's a 0, SB0, it doesn't have any arms. These galaxies do contain young stars and they're very rich in gas and dust. Just so you know, our galaxy is the Milky Way galaxy, and it is definitely a barred spiral galaxy. All right, so what's up next? We're going to pause this video right now, and you are going to take an in-class quiz. So I need you to take out a piece of scrap paper right now, and a piece of paper, and number it from 1 to 11. What I'm going to do is show you guys some pictures of galaxies, and you are going to decide whether you think it is spiral, elliptical, irregular, or a barred spiral galaxy. Okay, so we're going to pause the video and go ahead and do that. All right, we are back. So after that quiz, let's talk a little bit about galaxies known as the local group for number 4. The local group is a small cluster of galaxies that includes the Milky Way. It's like, in other words, like your local neighbors around your house. The diameter of the local group is about 10 million light years across. And how many members are in our neighborhood? The local group, 40. The largest galaxy in the local group is the Milky Way and the Andromeda Galaxy. And the most common type of galaxy in our little neighborhood of galaxies are the dwarf ellipticals. So that means like an elliptical galaxy that's really small, dwarf elliptical. So that's the local group. The local group, here's like an image of it. So if you look from far away, which this image right here is just of another group. This is not us. We can't see outside of our galaxy. We're in it, but we're looking at other galaxies that are nearby us. So that's an image, and it's just going to show you right here. If the Milky Way is right here, these are the 40 galaxies that are considered within 10 million light years of us. So the Andromeda is the next biggest galaxy next to the Milky Way. So again, looking out from our galaxy, these are some of the closest nearby galaxies that we would see through a telescope, but we can't, like, we're not in that picture. We're in the Milky Way, so we don't see ourselves outside. What I'm trying to say is these galaxies right here would be some of the ones that you're looking at in the photo. So that's called the local group. Number 5, what is the closest galaxy to the Milky Way? Canis Major Dwarf Galaxy. It's slowly being ripped apart by our own galaxy. So if you look at the image on the left right here, this is an infrared image of our galaxy. And you can see that Canis Major Dwarf Galaxy is really close to us. It's right there. So Canis Major is known as the dog constellation, the large dog. And the brightest star in the winter sky, named Sirius, is within this constellation. And so they're saying that Canis Major Dwarf Galaxy is within, you're going to find it really close to Sirius. All right, so that would be number 5. Other close galaxies, the Andromeda Galaxy is a galaxy you can see with the naked eye on a really clear night when it's visible. It is the closest spiral galaxy to the Milky Way. And then other close galaxies are the Sagittarius dwarf galaxy. It's an elliptical, and then the Large and Small Magellanic Clouds. So the Andromeda galaxy is close to the constellation Andromeda, which you see right here. And if you zoom in on that galaxy, there is a beautiful picture of that. So that galaxy is visible in the time of year when you'd see Pegasus. So we just passed that time of year. Pegasus is starting to set to the west. In the next several billion years, an artist's rendition of the Andromeda and Milky Way galaxies colliding. They actually think that may happen. And so frightening, very frightening. However, this band of stars is the Milky Way, that's us, and this is the Andromeda galaxy. So if you lived in the future, that might be what you see in the night sky. Frightening. All right, number 6, what could happen in a galaxy cluster that's larger than the local group? So the idea is the galaxies may collide and form strangely shaped galaxies, or they could have more than one nucleus. So in a galaxy cluster larger than the local group, where there's more than 40 galaxies, gravity is going to be really powerful, bringing them together. And so if you look at the stages here, the galaxies may over time pull closer together in this picture here on the left, and then get closer, start ripping material from each other, and eventually merge into one giant galaxy. So the idea is, do we see this out in our, our sky in the universe? The answer is yes. NGC, if you look 6872, is starting to collide with this object right here, which you can see the nucleus is becoming smaller and smaller. Number 7, what is redshift and why is it so important? Well, I know that we already did the Ballooniverse lab, but Edwin Hubble, he was a famous astronomer. The Hubble Space Telescope was named after him. He came up with the idea of redshift, showing that all galaxies that they could see through telescopes are moving away, all moving away, and so from planet Earth. And so it implies that our universe was once smaller. If everything's moving away and you see an explosion where everything moves away, then it implies that everything used to be closer together. So you graph this. Doesn't this graph look familiar? Because it should. This right here is a scatter plot showing that the best fit line through it, you could actually calculate slope and then find out the speed that the galaxies are moving and how old the universe is. So we call it Hubble's law. So Edwin Hubble called this red shift. Red shift means galaxies are moving away from us. Now, what is an AGN for number 8? AGN means active galactic nucleus. So what is an active galactic nucleus? It is a galaxy that emits large amounts of energy from its core, where a high energy object must be. So if you look here, this is like if we see galaxies, right, through telescopes, because the only one we see with the eye is Andromeda, right? But if we see galaxies and at their core, that bright cluster of stars I was talking about in the middle, if we notice that there's energy, high amounts of energy coming from them, then they have an active galactic nucleus. So that's what an AGN means. Number 9, I wrote, describe a radio galaxy and what makes them unusual. So a radio galaxy is a giant elliptical galaxy that emits as much energy in radio waves as it does in visible light. So we can scan space with looking for visible light, right? The kind we can see, but we can also use special instrumentation to find radio waves and radio energy. So when they scan space for all of that invisible spectra that you studied, they do find out that there are certain galaxies that are giving off insane amounts of radio waves, the kind of radio waves that we use to listen to music to on Earth. Why is that unusual? Because the radio emissions come from lobes that are opposite of the galaxy. So it makes them look like Mickey Mouse galaxies, all right, when you see it through radio waves. And they are linked by hot gases that travel at the speed of light. So I like to call these the Mickey Mouse galaxies, the radio ones, because you'll see the center right here. Look at the bottom image. And then they have clusters of radio waves on each side. Maybe Princess Leia would be a better description. Okay. Number 10, quasars. What are they? Well, quasars are objects that were discovered in the 1960s. They stand for quasi-stellar object, QSO, which means quasar. And they are star-like bodies that are celestial objects, and they emit more energy than our entire galaxy, the whole entire known galaxy. Now, they only have emission lines. Remember the 3 types of spectra? We talked about continuous, the rainbow, emission, the bright lines, and absorption, the dark lines. These galaxies only have emission because they're giving off insane amounts of energy. So we know of a quasar known as the Einstein Cross Quasar that is about 11 billion light years from Earth. You can see it right here. But this is an artist rendition right here, a red quasar versus a blue quasar, just showing the energy coming out from the galactic nucleus. Now, for number 11, how long does it take the light from a quasar to reach planet Earth? Several billion years. So, galaxies that have quasars are much different than galaxies without them because the centers of them are really, really bright. So, if you look at these images of the galaxies, you can actually see the middles of them are extremely bright compared to the pictures of the galaxies that you just saw. So, quasars set the age of our universe. They are the oldest objects that we know of. So, that is how we guesstimate the age of our universe at 13.7 billion years. So this wraps up the notes, not the notes, really, the pre-lab. And be sure at any time if you need to go back and watch this, you do. All right, we are going to move on to the lab.